Beaches. Beyond being tourist traps where sunburns are the norm, they serve multiple functions. They're economic drivers, they are home to unique species, and they serve as a boundary between a world of water and our lives on shore. For each of these reasons, it is critical to have an idea of how the structure of a shoreline can change over time. Such changes can critically impact the recreational activities and built environments on and around beaches. Jacob Marker's project takes a look at historical erosion at Neskowin Beach, Oregon, and what it means for people that visit and live near the beach. Jacob.
Okay. Hello, everyone, and thank you for coming. My name is Jacob Marker, and tonight I'm going to talk about beach erosion. Beaches, we all love them, but why are they important? Well, over 150 million people live within 1 meter of high tide. Beaches act as buffers to often densely packed and expensive coastal structures from waves. They generate substantial amounts of economic activity through tourism and offer us beautiful and bountiful areas for recreation. They also provide habitat to many plants and animals. At the same time, 70% of beaches today are thought to be eroding. So it's important we understand how these beneficial places are changing. Now, beach erosion isn't an inherently bad or good thing. Shorelines naturally evolve in response to a variety of environmental factors. Erosion can become a problem when populations live nearby, as illustrated by this picture of Waikiki Beach in Hawaii. The objective of this project was to use geographic data to analyze change to a beach near Neskowin, Oregon, and to do some risk assessment to the community and provide them with some useful maps and info. Tonight, I'll go over background information and then on to methods, results and analysis, risk assessment, and finally answer the question, what can be done? Welcome to our study area, Enchanting, Neskowin, Oregon. It's a small beach community not too far from Salem and Portland. Most homes are concentrated at the south end of the beach. The entire beach in front of Neskowin from headland to headland is about 15 kilometers, and I decided to focus on the southern 7.5 kilometers. I chose Neskowin because it was designated by the USGS as a place with significant beach erosion, and because I read of some concern about erosion in local newspapers. A few pictures to give you an idea of what this place looks like. First off, I'd like to go over the fundamental causes of beach erosion, and I'll tell you there are three. Number one, a relative rise in sea level. Number two, a deficiency in the sediment budget. And number three, an increase in wave intensity or a shift in wave patterns. Associated with this is El Nino events, and I'll discuss that shortly. Additionally, human interference can be to blame through dams, jetties, or the removal of stabilizing vegetation, but that doesn't apply to Neskowin. When discussing sea level rise in the Pacific Northwest, the tectonic context becomes important. Here, the Juan de Fuca plate is actively subducting beneath the North American plate. As tension builds before an earthquake, the crust deforms. Some areas experience uplift and others subside. As a result, it's possible for relative sea level to be falling while the actual water volume of the ocean is rising. The graphic at the right is showing relative sea level rise along the Pacific Northwest. Neskowin is undergoing relative sea level rise, but only at about 1 millimeter per year. So even though sea level rise is likely to become a more important factor in the future, it probably isn't the driving factor if we see beach erosion at Neskowin. These features on Neskowin Beach became visible during some winters in the 1990s. Researchers found out that they weren't stumps, but in fact the middle and tops of trees that had been preserved after a huge subduction zone earthquake caused quick subsidence of the land and buried part of the forest. It's called the Neskowin Ghost Forest and is a reminder of the power of these earthquakes, and also that an event like this is a serious threat to the Pacific Northwest and could cause, among other things, some instant beach erosion. Sediment supply is also an issue for Oregon beaches. From the last ice age to about 2,000 years ago, Pacific Northwest shorelines were far more seaward of present positions and continuous from the Columbia River on down. Today, many beaches are bounded by rocky headlands, like the Pocket Beach you see up here, preventing replenishment from Columbia River sediment. Thus, there are few modern-day sources of sand for Neskowin Beach. And on to what the USGS deems to be the most important factor causing erosion seen at many Pacific Northwest beaches, waves and El Nino. The Oregon coast experiences some powerful winter storms, and the USGS has shown that at least since the 1980s, storm severity and deep water significant wave heights have been increasing. Larger storms can push sand along a beach and also pull sand out to sea. In addition, El Nino events elevate winter sea levels by tens of centimeters and shift the storm tracks, leading to hotspot erosion at some beaches. So let's get into the methods of this project. These methods are based off ones developed by the USGS in their national assessments of shoreline change. This project differs in some key ways, however. While the USGS report covers large regions and reports rates for an entire beach in a table, I wanted to look at where the erosion was occurring in detail and also create some maps that would be accessible to the community. Also, in their assessment of the Pacific Northwest, the USGS used a 2002 LIDAR-derived shoreline. I decided to use 2014 imagery-derived shoreline because it added 12 years of time, and I wanted to try these methods using current high-res imagery. I'll go through some of these methods now. After acquiring your data, the first step is to make sure that everything lines up. On the left, you can see the before image of the 1927 historical map overlaying the 2014 imagery. Haystack Rock is far to the north of where it should be. And on the right, you can see the after image where everything has been nicely georectified. This slide is just to show some of the equations that go into calculating uncertainty in shoreline position. It's really important to take the effects of tides, digitizing, and a whole host of other effects or other uncertainties into account when you're doing this kind of thing. For 150 years, people have used the high water line as one proxy for shoreline position because it's easy to visually identify. So that's what I use. Here you can see the final digitized shorelines. After digitizing and calculating uncertainties, I worked through a number of steps with something called the Digital Shoreline Analysis System to produce these results. This is a map showing shoreline movement rates from 1927 to 2014 for the area. North is to the right. Rates are given in meters per year, and it's important to note that these are just the average rates between two endpoints. You can't assume that the change progressed evenly at a steady rate. The overall trend of the beach was an erosional rate of 0.09 meters per year. The uncertainty associated with each transect was plus or minus 0.28 meters per year. The brighter red transects show significant erosional rates, meaning rates faster than the uncertainty of 0.28 meters per year, and the bright blue transects show significant progradation, or seaward movement of the shoreline. 49 transects showed significant erosion compared to just 24 showing progradation. So next, I'm going to zoom in to the north of the beach. Here we are at the northern third of the study area. This third of the beach showed the most progradation of anywhere. And one possible explanation of why we see this is that strong El Nino storms come from the south and end up pushing sediment to the north, but you would have to continue this study up another 7 kilometers to the north headland to really investigate that further. This middle third of the beach showed lots of erosion. The area on the far left of the map had the fastest erosional rates with 0.67 meters per year, which equates to about 45 meters of beach loss. So next, I'll zoom in on that hotspot. The geometry of this hotspot looks very much like that of a rip current embayment. Rip currents are rivers or jets of seawater return to the ocean after waves break, and they can cause some localized erosion. These so-called rip current embayments can be particularly large and frequent in El Nino years. This southern third of the beach showed some significant erosion in the center there, which actually found to be the most disconcerting because of how close it is to the main community, which is right beneath it. I decided to focus in on this area, and there was just enough LiDAR coverage to get an idea of what it looks like three-dimensionally. Here, dark green is the lowest elevation, and dark orange is the highest elevation. When just looking top down here, it seems that the houses are at high risk of being flooded, but using LiDAR, you can see the houses rest upon a large dune. By measuring from the high water line to the base of the houses, I was able to tell that even a record-breaking storm surge would not likely overtop the dune and flood the houses. The main concern of the community should be protecting this kind of foundational dune from erosion. This is really just to show how cool LiDAR data is. I've changed the colors, and in the top image you can actually see the waves breaking onto the beach and really clearly the houses on top of the dune. This is a digital elevation model of the study area. In this map, I have classified the elevation, and you can see the Neskowin Dune, again, where almost all the houses are, in light green. So using a method called linear combination, where you combine different maps of factors, in this case, risk factors, into a single map, I created this possible risk assessment. I used elevation and proximity to eroding transects as risk factors. Ideally, you could add in many more relevant factors and really improve this map. Of interest, the only bridge on and off the dune, it's labeled up there, is in a high-risk zone because of its low elevation. If they can't cross the bridge, the community is effectively trapped on that dune. This bridge has been damaged before, and it seems like it'd be worthwhile to further investigate how protected it is. This is showing that you can export these type of maps and look up exactly where you live or are thinking of buying a house. I'll quickly talk about what can be done to help mitigate this erosion. In 2014, Neskowin produced a community adaptation plan, and the first thing they looked at were jetties and groins. Those are shore perpendicular structures used to trap sand. Fortunately, they are expensive, not effective on beaches with rip currents, like we saw in Neskowin, and can further the erosion up or down the beach. Breakwaters are shore parallel structures, you can see on the right, and are designed to reflect wave energy. However, the committee estimated that it could cost up to $370 million per mile to construct, and further analysis would have to be done to ensure that they would actually work. And with both of these, you also end up with very unnatural-looking shorelines. Beach nourishment has been used in places like Hawaii and the Jersey Shore, but again, it would be expensive for Neskowin as there are no nearby sand sources, and the beach would have to be continually replenished. Every few years, you'd have to bring in more sand. The most viable option for Neskowin is likely riprap. Riprap is a series of interlocking boulders installed to prevent erosion. You can see the right image. It ain't pretty, but it works pretty well. The image on the bottom left occurred in Neskowin in the winter of 2008, partially due to the fact that it was undergoing riprap repair when a large storm struck. Almost all Neskowin beach houses do have installed riprap. The community is considering adding 8 feet of reinforcement. You can see the top left image, which aside from simply leaving, may be one of the only options for residents. This very cool looking house was recently constructed and put on the market. Is it a good investment? Probably not, but you'd have to look at exactly where it is, and all I can recommend is that you do your homework before buying a coastal property. And for the residents currently in Neskowin, I recommend that they stay as informed as possible and that they come up with some solid plans for future scenarios. To conclude, this project found hot spots of erosion on the beach and a little progradation in places. The Neskowin Dune certainly does seem at risk for erosion. The USGS suggests that ever larger storms and El Nino events are the primary cause of the change we see, although sea level rise will likely be a bigger factor in the future. There are many ways in which this project could be expanded. The first thing I'd love to do is add in shorelines from other years where data is available to really hone in on the timing of the movement we see. And although aerial imagery is effective, the recent use of LiDAR to derive more objective elevation datum-based shorelines is really attractive. And as LiDAR data from more years becomes available, I think the idea will be to use these methods, but to compare LiDAR-derived shorelines with other LiDAR shorelines. With sea level and storm severity projected to rise into the coming century, it will become even more important to study the Earth's evolving shorelines. I hope GIS and this project can provide 2 means of helping. Thank you, everyone, for listening, and thanks to all the fantastic people who helped me along the journey. Any questions? Okay, yeah.